Ayubowan students, and a very warm welcome to Study Hub Sri Lanka.
So glad you could join me. Today, we're going to dive into a really fascinating and important chapter, mixtures. This is a topic that's all around us, from the air we breathe to the food we eat, and understanding it is absolutely key to mastering your chemistry syllabus.
So what's our plan for today? Well, first, we'll get a clear idea of what a mixture actually is. Then we'll look at its two main types. After that, we'll get into the more practical side of things, how to measure what's in a mixture and, the most interesting part, how we can separate them back out. And of course, we'll wrap up with the key takeaways you need to know. Right, let's get started.
Okay, Section 1. What exactly is a mixture? You see, our natural world is mostly made up of mixtures, not pure substances. Just think about it for a second. The soil under our feet, the seawater at the beach, even the nice cup of tea you had this morning, all of them are mixtures. So what's the official scientific definition? A mixture has two or more components that are not chemically combined. Now, pay close attention to this next part. It's the most important bit. They can be separated by physical methods. This means the original things you put in are still there. They keep their own identity. They're just, mixed together.
These examples here really make the idea clear now. Look at cement mortar. It's just sand, cement, and water physically stirred together. Or think about baking a cake. You have sugar, flour, butter, so many different components. And even the air we're all breathing right now is a mixture. See, we are literally surrounded by mixtures every single day. Okay, now that we know what mixtures are, how do we start to organize them? Well, it turns out that all mixtures in the world fall into two main types, homogeneous and heterogeneous.
So, the big question is, how can we tell the difference? What's the secret? It's all about how evenly the components are spread out. Are they mixed together so perfectly that it looks like one single thing? Or can you still see the different parts? This slide breaks it down perfectly. On the left, we have homogeneous mixtures. A perfect example is salt dissolved in water. The composition is completely uniform. You can't see the little bits of salt, and every single drop of that water will taste salty. That's why we also call these solutions. But on the right, you have heterogeneous mixtures, like clay mixed with water. The composition is not uniform. You can see the bits of clay floating around, and the bottom of the glass will probably be much muddier than the top. The properties are different from place to place.
Let's just quickly get these important words straight. A solution, like we just said, is a homogeneous mixture. It's made of a solvent, that's the component you have the most of, like the water in our salt solution, and one or more solutes, which are the substances that get dissolved, like the salt itself. Simple as that.
All right, let's move on to our next section. We know what mixtures are, but how do we describe them scientifically? We need to be able to measure their composition. And this is so important in the real world, Mena. Think about a doctor preparing medicine or a farmer mixing insecticide. Getting the composition exactly right is absolutely essential.
Now, there are a few different ways we can express composition, like mass fraction, volume fraction, and so on. For our lesson today, we're just going to focus on two of the most common ones that you'll definitely see in your lab work.
First up, we have mass fraction. Now, don't let the name sound complicated. It's simply the mass of one part of the mixture divided by the total mass of the whole thing. And since it's a ratio, a comparison, it has no units. It's a really easy way to describe how much of something is in a solid mixture.
And here's the formula. It's so simple to remember. If you want the mass fraction of component A, you just take the mass of A and divide it by the total mass of everything together. It's very logical, don't you think?
Now, when we talk about solutions, especially in chemistry, we almost always use concentration. This is the amount of moles of the solute packed into 1 cubic decimeter of the solution. You are going to see this unit, moles per cubic decimeter, all the time when you're doing experiments and preparing solutions in your school lab. It's a big one. Okay, now for the really fun part. Section 4 is all about separation techniques. Since mixtures are only physically put together, it means we can also physically take them apart. So let's find out how we can unmix a mixture and get our original ingredients back.
Here are some of the most common ways to do it. You already know some of them, like sieving sand to get out the big stones or filtering your tea to get the leaves out. But in the lab, we use some more advanced techniques, like distillation and a very cool one called chromatography.
So, what's the secret to all of this? The main principle is this. Every single separation technique works because it takes advantage of a difference in the physical properties of the components. Is one thing bigger than the other? Does one boil at a lower temperature? Is one magnetic? We use these differences to pull them apart.
Let's look at a really important example, simple distillation. This is perfect for separating a liquid that evaporates easily, like water, from something that doesn't, like salt. First, you heat the mixture. The water turns into steam, leaving all the salts behind in the flask. Then, that steam travels through a cold tube. We call it a Liebig condenser, which cools it down and turns it back into pure liquid water that we can collect. This is exactly how we make distilled water for labs.
And here's another really powerful one, chromatography. I bet you've actually done this without even knowing it. Have you ever put a drop of ink on a piece of wet paper and watched the different colors spread out and travel up the paper? That's paper chromatography. It separates things based on how fast they move through a material. It's an incredibly useful tool in modern science for separating very complex mixtures.
And that brings us to our final section for today. We've covered a lot of ground, so let's quickly review the most important points from our lesson. This is the stuff you really need to lock in for your exams.
So, let's recap. What did we learn? First, mixtures are just physical blends, not chemical combinations. Second, we can sort them into two big groups, homogeneous, where everything is perfectly mixed, and heterogeneous, where you can see the different parts. We also learned how to describe what's inside a mixture using things like mass fraction and concentration. And finally, we saw that we can separate them using physical methods that take advantage of their different properties.
Now, before we finish up, here's a little something for you to think about. You know our country is famous for its spices, right? Especially our cinnamon. So now that you know about separation techniques like distillation, can you figure out how we extract those beautiful essential oils like cinnamon oil from the leaves and the bark? It's a perfect real-world example of what we learned today.
Thank you so much for joining today's lesson, my dear students. I really hope you found it helpful. We'll meet again very soon with another explainer for your science subject. And please, before you go, don't forget to subscribe to our channel, Study Hub Sri Lanka, and make sure you click that little bell icon. If you do that, you'll get an update immediately whenever we post a new lesson for you. Keep up the great work with your studies, and I'll see you in the next one.